All right, class, now we're going to start 7.4. In 7.4, we're going to add, subtract, and multiply radicals, but this video is only going to be on adding and subtracting radicals. So first we'll start out with something like this. If I have 4 square roots of 11, and I want to add that to 8 square roots of 11. Right here, this is basically a coefficient. Okay, and remember that what's under here is the radicand, and that the square root symbol itself means that thing to the 1/2 power, right? Or to the fractional power, whatever it is. Let's say that this is n, whatever that is. So this is what it means. Okay, so if I said to you, hey, can we add 4x plus 8x? Then you'd be like, well, yeah, those are like terms because they're both x's to the power of 1. So then you would just combine their coefficients, the 4 plus the 8, and you would get 12x. Well, what is a like term or a like radical? Like radicals, by definition, have the same index and the same radicand. Now, this is no different than a like term. Like terms have the same variable or base and the same exponent. Since indexes are exponents or fractional exponents, then basically a like radical is a like term. So I've got a base here and I've got an exponent to the 1/2. So these are like terms. So if I were to add these when what's inside the radicand is the same and the index is the same, then I would just say this is 12 square roots of 11 in the exact same way that I would say this is 12x. So we also, when we add the coefficient or combined coefficients. Okay, not exponents like we did before. Okay, so if we had something like 5 cube roots of 7x, and I wanted to subtract 8 cubed roots of 7x, then the question here is the radicand the same, 7x and 7x are the same, and the index are the same, 3 and 3 are the same. So then I'm just going to combine these coefficients. 5 minus 8 is going to give me a -3, and this is going to be still cubed roots of 7x. So if the radicands are the same and the index are the same, we just combine their coefficient. Tell me, could we add together 3 4th roots of x plus 9 5th roots of x? So these have the same base or the same radicand, but they do not have the same index. So these are not like terms. You can't simplify that any further. Another thing that we want to look at here is if we have the same, say like I had 2x square roots of 3x, and I wanted to subtract 5 square roots of 3x. So we say, hey, well, 3x is same radicand, index is 2, so same base, same radicand, same index, but can I combine these terms? If we didn't have this, and I asked, hey, can we combine 2x minus 5? You would all say, well, no, because they're not like terms. So keep in mind that what's on the outside also has to be like terms. I can't combine these. So these cannot be combined. Okay. But if I had 2x square root of, say, let's change these. Let's say if I had like 5x square root of, I don't know, 10y minus or plus, say, 7x square root of 10y. This is the same radicand, same index, and on the outside, these are like terms. I can combine 7x and 5x. So when I combine these, I would get 12x square root of 10y. Okay, just like if I combine the 5x plus the 7x, I'd just get 12x. So my coefficients combine the same way. So on the outside, you also have to have like terms. Okay, so let's work several of these that don't have the like terms. What we'd have to do, like radicals, is you have to simplify them first. So you want to simplify first. We're going to simplify first using this rule, the product rule, and the quotient rule. Well, that was an ugly one. Let me try that one again. It's not much better, but that's all right. Okay, is the same thing as this. Okay, so we're going to use these rules that we just worked on in last section to add and subtract these. So if I were given the square root of 50 plus 5 root 18, I'm going to look at this and say, well, 50 and 18 aren't the same, but what could I do to 50 to simplify it? What could I do to 18 to simplify it? With 50, remember that tip I gave that you should try dividing stuff by 2, 3, and 5 to see if it's a perfect square or cube that you recognize. If I divide this by 2, I get 25, and that's our ticket. 25 is a perfect square, so I'm looking at the square root, and these are the factors inside, right? 2 I can't do anything with, so it has to stay under, but this 25, the square root of 25 is 5. Okay, and this 18, again, I'm going to look and say, oh, well, that's 2 and 9. Hey, that's a perfect square as well. So I'm going to have a 5 outside already. Remember, the relationship between the 5 and the square root is multiplication. The square root of 2 is going to stay in, but the square root of 9 is 3. It's going to come out. But the relationship here, again, is multiplication. So this is going to be plus 15 square roots of 2. Well, now they have the same index and the same radicand. Now I can combine their coefficients for 20 square roots of 2. So that is how you would add these radicals. I just want to go through several more examples here. And maybe pause the video and try to work through some of these on your own. What if I had a cubed root instead? Well, this doesn't change anything. I'm still just going to ask myself, hey, do they have the same radicand and the same index? So these are all the same index, but first I need to look at 54 and say, can I simplify it? If I do 2, again, I'm always going to try like dividing by 2, 3, and 5. Those are the easiest ones to find perfect squares. So 54, or perfect cubes, is 2 times 27. 27 is a perfect cube, so I'm just going to look at this like the square root of 2 and the square root of 27 separately. The square root of 2 I can't simplify, but sorry, the cubed root of 2 I can't simplify, but the cubed root of 27 I can. The cubed root of 27 is just the number 3. Again, that's related through multiplication. Lots and lots of different ways to simplify these. Remember, what we're looking for is 3 of the same factors, so I'll do this another way as well. So factor down to 2 and 27, and 9 and 3, and 3 and 3. There are 3 of these, so 1 can come out. But this one is all by itself, so it has to stay under. This 16, again, I could factor to this 2 and 8, which 8 is a perfect cube. It also factors to 2 and 2. There are 3 of these, so a 2 can come out. There is already a 5 outside of here, and this lone 2 has to stay under. Negative 5 times the 2 that we took out, because there were 3 of them, is a negative 10 cubed roots of 2. Now this one, it can't be simplified because I can't factor 2. So I'm just going to look at all of these and say, hey, are these like terms? Well, they have the same radicand and the same index, all of them. So I'm going to combine their coefficients. Remember that even though this doesn't say a number, this is like having one of those. So I'm going to do 3 minus 10, which is a negative 7, plus 1, which is a negative 6. So this would be negative 6 cubed root 2. And that's how this would simplify. So again, I'd like to give you a couple here to do. So these next few, why don't you try doing them on your own before you look through the solution. So we've got square root of 20x minus 6 square roots of 16x plus the square root of 45x. So go ahead and pause the video, take a minute to work through this one on your own. And hopefully this is what you did. You did something like this. You said, okay, well, I'm going to try to factor this with 2 and 10. That's not very helpful. So let's try 4 and 5. That's helpful because 4 is a perfect square. So this 4 is going to come out and be a 2. And I'm going to have this 5 stay under and this x also stay under. That's as simplified as the square root of 20x can get. So now I'm going to move to this next one. 16 is a perfect square. There is already a negative 6 out here, and again, this relationship is multiplication. When I pull the 4 out, it's going to be related to multiplication. This x, though, it can't come out because there's only 1. So this is going to be a minus 24 square root of x. Looking at this next one, I'm going to say it's not divisible by 2, so I'll try 3. I get 3 and 15. That's not too helpful, so I'm going to try 5. And I get 5 and 9. That works because 9 is a perfect square. The 5 I can't do anything with, so it has to stay under. And this x I can't do anything with, so it has to stay under. But 9 is a perfect square. It'll come out and be 3. And I'm going to be adding that. So now I'm going to look and say, hey, can I combine these? Well, these two have a 5x and their index is 2, but this one does not have the 5. So this is not a like term. So only these two are like terms, and they can be combined. So 2 plus 3 is 5 square roots of 5x minus the 24 square root of x. So this here would be our answer for this one simplified. Okay, I'm going to give you a couple more. You can pause. Okay, go ahead and try 2 square roots of 50 minus 3 square roots of 125 plus the square root of 98. So go ahead and pause and simplify and combine these if you can. All right, so hopefully, again, you're going to take this 50 and break it down to 2 and 25 because 25 is a perfect square. There's already a 2 out here, so when I bring the 5 out, that's a perfect square. This 2 is going to stay under, so I will have 10 root 2 here. So this 2 came down, this 25 came out to this 5, and this 2 stayed under. Now I'm going to look at this 125. It's not divisible by 2, so I'm going to try 3. 3 isn't gonna work. It'll go in 41 times with change, so we've got to go for the 5. So again, we're going to try this 2, 3, and 5. This is 5 and 25. So again, this is a perfect square. There's already a 3 out here. When I pull out this 5 from that 25, I'm going to get a 5 out there, and the square root of 5 is going to stay under. I'm going to multiply these two values together and get a negative 15 square root 5. Okay, then I'm going to look at this 98. I'm going to start with a factor of 2. We get 2 and 49. 49 is a perfect square, one of them that you should have memorized. The square root of 49 is 7. So 7 is going to come out. This 2 has to stay under. So there's nothing more that I can do to simplify that. So when I'm looking at these, I'm going to say, hey, this and this are like terms, so I can combine them. They're like terms because they have the same radicand of 2 and the same exponent or the same index, which is also 2. So 10 plus 7 is going to give me 17 square roots of 2 minus a 15 square roots of 5. So this here is our answer for this problem. I want to do 2 more problems with you. So far we've pretty much used this product rule here to simplify, but I want to give you a few where we're using the quotient rule. And let's see, we're doing a little tricky stuff, so we'll see here. If I had square root of 75 over 9 and I want to subtract the square root of 3 over 2, first I want to simplify any radical that I can. This 9 is not under square root, so the denominator is just 9. If this said square root of 9, then I could write this all over 1, but it doesn't, so it has to stay on the outside. It's just a value of 9. Square root of 75 can be factored to 3 and 25, and the square root of 25 is 5. So on top here I'm going to have 5 square roots of 3 over 9. And here the square root of 3 I can't do anything with. Now if I want to combine these, not only do they have a fraction, but they have radicals. So this radicand is the same, 3, and so is the index, is 2. But I can't add or subtract these fractions without them having the same denominator. So I actually have to find an LCD here. And in this case, the LCD is 18. 18 is the smallest number that both 9 and 2 goes into. So I would need to multiply this fraction by 2 to get the bottom to be 18, and this fraction by 9 to get the bottom to be 18. Remember, whatever we do to the bottom, we have to do to the top. So this new fraction here is 10 square roots of 3 over 18 minus 9 square roots of 3 over 18. Now that they have the same denominator, I can go ahead and combine the like terms up top. So 10 minus a 9 is just going to give you 1 square root of 3. But 1 times anything is just itself, so we're not going to write that 1, and this is going to be over 18. Now a lot of people have this question, hey, can't I simplify this 3 with this 18? Well, no, because this 3 is being raised to the 1/2 power, and this 18 is being raised to the 1st power. So unless they're both underneath, like this, then you can't simplify them, right? I could write this like this and get a 1/6 and simplify it like this, but one of them is under a radical and one of them is not. So in this case, we can't simplify any further. So here would be our answer.